Hi students, in today's session we are going to discuss another technique which is used for the synthesis of nanomaterials. It is called pulsed laser deposition. So it is a deposition method used for thin film deposition as well as nanomaterial synthesis. Here, as the name suggests, a high power laser pulsed a high power pulsed laser beam is focused inside a vacuum chamber to strike a target. That is, a pulsed laser beam is made to strike a target of the desired material whose film or nanomaterial is to be formed, and when the laser beam strikes the target, it causes the target material to vaporize, and these target atoms then deposit on the substrate. Okay, so there is a high power pulsed laser beam which is placed inside the vacuum chamber, and it's allowed to strike a target the target is made of the desired material which has to be coated on the substrate or whose nanoparticles have to be synthesized, and the pulsed laser beam strikes the target. The target material gets vaporized and the target atoms then get deposited on the substrate. This is how the pulsed laser deposition takes place. Now, the deposition process takes place in ultra high vacuum or in the presence of some background gas of certain pressure. Usually, some neutral gases such as argon at some desired pressure are used. This is used to control the deposition rate as well as the film composition. Whereas, if you have to form oxide or nitride films, then the atmosphere is made of oxygen or nitrogen. That is, reactive gases like oxygen and nitrogen are used to deposit the oxide and nitride materials. Now, this method is very useful in depositing materials of complex stoichiometry like YBA2CU3O7. So, this material has a complex stoichiometry here. Yttrium, barium, copper and oxygen are in the ratio 1 is to 2 is to 3 is to 7, that is, which is a complex stoichiometry. So, it is very useful in depositing materials having complex stoichiometry. So, this method is especially useful for forming multi-element oxides, nitrides, metallic multilayers and various superlattices. Now, let us study exactly what is the basic setup of a pulse laser deposition chamber. What all things are contained, or what all setups are there inside the pulse laser deposition chamber. So, I'll show you a figure. The schematic diagram has been scanned from the textbook Introduction to Nanoscience and Nanotechnology by K.K. Chadobadhyaya and A.N. Banerjee, which is our book of study. So, the basic setup of the PLD consists of a rotating disc. This is the rotating disc on which the target material is set. So, there is the rotating material on which the target material is set. This rotating disc is attached to a cylindrical rod, which allows the rotational motion of the target. The target can be rotated as well as it can be moved up and down along its axis. So, along the axis, it can be moved up and down or forward and backward along the axis. The target material can be moved. Now, here, this is a vacuum chamber. Then, this is the substrate where the substance has to be coated. And the laser beam falls on the target through this port. Now let us see the exact processes that take place here. So the process of laser deposition is divided into 4 stages. The first stage is the laser ablation of the target material and creation of plasma. What is meant by laser ablation? Laser ablation means the process of removing material from a solid surface by irradiating it with a laser beam. So the laser beam falls on this target material and the target material gets removed from its surface. This process is called laser ablation. Now at low laser flux, if the flux of the laser is low, then the material gets heated because it absorbs, the target material gets heated because it absorbs the laser energy and it evaporates. Whereas at high laser flux, the material is converted into a plasma. The target material gets removed as such and it forms a plasma. Next stage in the pulse laser deposition process is the dynamics of the plasma. That is, the ejected species now expand into the surrounding vacuum to form a plume. This is the laser plume. Plume means some kind of vapor in the shape of a feather like having a feather like shape. That is called a plume. So here a laser plume is formed, which consists of the atoms, molecules, electrons, ions, clusters, etc. of the ejected target material before it gets deposited on the substrate. So what happens in the second state? The ejected species expand into the vacuum to form a plume. The third stage is the deposition of this ablation material on the surface of the substrate, and then the nucleation and growth of film on the substrate. So these are the 4 stages in the pulse laser deposition process. Now, what are the advantages of this method? It's conceptually very simple. That's the first advantage. A laser beam vaporizes a target surface, producing a film having the same composition as the target. Either it vaporizes the surface, the laser beam, if it has low flux, it will vaporize, or if it has higher flux, it causes laser ablation, and the ablated material gets deposited on the it forms a plume, and later it gets deposited on the substrate to form the film. This method is very versatile. That is the second advantage. That is, many materials can be deposited, and the deposition rate can be controlled by adjusting the laser pulses. The next advantage is it is a very fast process. Very fast process means high quality samples can be grown in just a matter of 10 to 15 minutes. And the last advantage, it's scalable. That is, volume production can be done. That is, large scale production of the thin film or the nanomaterial can be done using this procedure. So it is a scalable process. So these are the advantages. So I hope the pulse laser deposition technique for producing thin films and nanomaterials is clear to you. So in this method, a high energy or a high power pulsed laser beam is focused inside a vacuum chamber onto the target material. The target material then undergoes laser ablation to produce an ejected species. The ejected species then form a plume. The plume then gets deposited on the vacuum on the substrate where the thin film is grown. And this method is highly advantageous because it's conceptually simple, it's versatile, it can be used to grow materials having complex stoichiometry, it's fast, and it's scalable. So I hope pulse laser deposition is clear to all. If you have any doubts, please do contact. Thank you.